All right, so this is going to be a video of basically converting from integral notation to Riemann sum notation and vice versa. So to do that, I'm going to kind of use an abstract example here. So I have this graph here. It's a continuous function, a graph of a function in red here from A to B. And basically what we're looking for is how would I convert this integral? So if you can imagine we're looking for the area between A and B underneath this red graph here. So we're basically looking for this whole part right here. There's an integral that represents that, and it basically looks like this. So basically we're going to be looking for how to convert this integral to basically to the Riemann sum notation. So that's basically what this video is going to be all about. It's helpful. There's some AP Calc questions that involve this type of thing, so it's kind of good to show how to do this. All right, so for the first thing I'm going to do is I'm just going to find the area using Riemann sums, but I'm going to be doing it with one rectangle. I'm just going to do left-handed sum for this. I'm going to do one rectangle, two rectangles, four rectangles, and then we're going to go into infinite rectangles. And the reason why we're breaking down the rectangles like this is because you kind of start to see a pattern, and that kind of leads to how to convert this this integral notation to that sum notation that we're looking for. So we are going to say that n is equal to the number of rectangles. All right, so the first one that we're going to do is we're going to do one where it's n is equal to one rectangle. All right, so to figure out that area, what we're basically going to do, let's see here. We are going to, so I'm going to kind of draw this in here. So we're going to, if we have one rectangle and we're doing left Riemann sums, it's basically going to be the rectangle from here all the way to here and down. Okay, so that's basically what we're going to be looking for when we find this area. So I'm going to write A is approximately equal to, okay, well this rectangle right here, this yellow part, is basically going to be equal to the height, and this height right here is just going to be f of A, so I'm going to write that in, and this width right here is just B minus A. So what I'm going to write right here is I'm just going to write f of A times B minus A, and that's going to be in parentheses. All right, so that B minus A basically just represents the width of each of those, of this rectangle. All right, so now we're going to do another rectangle, only this time we're going to do, we're going to do another area, but this time we're going to do two rectangles. Okay, so this one, the A is going to approximately be equal to, okay, now we're just going to do equal width rectangles on this. So the rectangle is going to look like the following. Okay, I'll try to draw these in with green here. So this rectangle, it's going to be basically split here because it's going to be equal width. So this coordinate right here is in the middle of this B minus A. So right here it's B minus A over 2. So this is going to be the shift over here, the width is just going to be B minus A, just like we have right here, this B minus A. Only it's going to be B minus A over 2 because you're dividing it in half. So it's going to be whatever that A value is plus that B minus A all over 2. Okay, so that's what this value right here is going to be. So I'm going to draw the rectangles because we're going to do two rectangles here. So we got this right here and then down. So we have that first rectangle here. Then we have this second rectangle. We're just doing left sums here. So we're going to have those two rectangles right there. So back to our area approximation, you are going to have that first rectangle. It's just going to be f of A times, okay, so f of A is that base. Now we have to do, or I'm sorry, is the height. The base right here is just going to be this coordinate right here minus this A. So it's just going to be B minus A over 2. So I'm going to just write that in there, B minus A all over 2. Okay, and then we're going to add that second rectangle over here, and that's basically just going to be f of, now this time it's going to be f of A plus B minus A all over 2 times, okay, so that's going to basically the height here, and then we're going to be looking for this width right here. Now the width is actually the same thing as this B minus A over 2 right here, so I'm just going to write that in here because we have equal width. We don't need to bother with anything else. So right there we have the area approximation if we're using two rectangles. Okay, I'm going to shift this down a little bit just so we can fit in 4. And I'm going to do 4 just because it's just easier to divide up with what we have and I don't have to redraw anything. All right, so we're going to say n is equal to 4. Okay, so for this one we have to kind of break up these this rectangle a little bit more. We have this value right here, and this value right here. So you can kind of imagine how our rectangles would be. It's just basically going to be like this. Hopefully you can follow along with this. And then this value right here down to that center part again. And then from here, but we're stopping right here for that width. And then for this oops. And then just right here for this last rectangle right here. So we have all those rectangles right there. Okay, the one thing that I didn't write in here, because there's just not a lot of space, is what the coordinate for this x value is here and what the x coordinate for this value is here. So I'm going to kind of write these. So I'm going to do is kind of zoom in here so I can write these a little bit easier. So basically, each one of these widths is just going to be b minus a over 4. So it's b minus a over 4 here, here. So it's basically going to be b minus a over 4 here, this part right here, this part right here, and this part right here. So then if you added up b minus a plus 4, or b minus a over 4 times, it would just be b minus a, which is the whole thing. So this value right here is basically just going to be a plus b minus a all over 4. So that's what this thing is going to be right here. And this one, and you can kind of figure this out on your own, is just going to be a plus b minus a all over 4, but this whole quantity right here is going to be multiplied by 3. All right, so now we're going to find the area, that area approximation using those 4 rectangles. So I'm going to go right here. I'm going to write a is approximately equal to, all right, this first one is still going to have that height of f of a times, okay, they're all equal width, so that base is going to be b minus a over 4. So this part right here basically is b minus a over 4. All right, then I'm going to add f of a plus b minus a over 4. And then again, I'm going to multiply by that b minus a over 4 here. And then I'm basically going to repeat that for all the other rectangles. So these are the first 2 rectangles real quick. I'm just going to do the other 2. All right, so then we have all of those area approximations right there. Tried to color code it as much as I could. Now, you should hopefully see a pattern here. We're going to actually use this pattern to figure out what would happen if we are using infinitely many rectangles that are infinitely thin. All right, so the first thing we're going to do is we're going to try to address what this pattern is. Okay, so hopefully you see right here, it's f of a plus 0, basically, because it's just f of a. And then it's times this equal width. And the equal widths match each time. So you could see one here, 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 and here. And if you notice, they're in every single one of these. We have one here and here, and then we have one here. So if you notice, they all match, and they all are divided by however many rectangles we're using. So if we're using 1 rectangle, you divide by 1. If we're using 2 rectangles, we're dividing by 2. If we have 4, we're dividing by 4. So what I'm going to do is actually define what that value is. So we're going to call it delta x, and it's basically just going to be equal to b minus a all over n being the number of rectangles, as it says right here, and I forgot the s. Okay, so what we're going to do, what makes it simpler with that is we can just use delta x from now on rather than writing that b minus a. Okay, the next pattern that I want you to see is, if you notice, the first input for the f right here is just a. If you notice, that's a for all of them. And then as soon as you have another one, you're basically just adding that delta x each time. Okay, if you notice, we're adding a delta x, and we're adding a multiple of delta x. This one only has 2, so we're adding 1 multiple of that delta x. This one, we're adding 1 multiple here, and then if you notice, there's a little 2 here. Okay, the 2 and the 4 cancel, so that's how you get this b minus a over 2, this part right here. But if you notice, it goes 1, 2, and then this other one right here is 3. So we're going to use that with our summation to basically figure out what this summation notation would be if you're using an infinitely many rectangles. All right, so here we go. We are going to be approaching infinity, so I'm going to say n is approaching infinity. Now, when you get infinitely many rectangles, what you're basically looking for then is the exact area, because if you can imagine, we're getting smaller and smaller rectangles, and it's fitting perfectly underneath this curve, so it's going to be equal to that integral. All right, so here we go. So if I take the area, it is going to be equal to, okay, we have n going to infinity, so we are going to need limits on this, so we're going to have to put that limit as n approaches infinity in here, and we are going to add up those infinitely many rectangles. Now I'm going to use I as basically our index for what we're adding. So we're going from 1 to n is going to infinity. Okay, so we're taking n going to infinity. That's how many rectangles we're using. And we're going to add up whatever the function is. And if you notice, every single one of them starts with a. So every single one of these patterns, a, there's an a here, 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 and so on. So we're going to have that a there. And then we're going to add our I. But if you notice, our I starts with 1 here. The I for this one is actually 0. If you notice this first part right here for each of these, it's going to be 0. So we need to actually subtract off 1 from this and then put it in parentheses. Okay, then if you notice when I is 2, it's going to be 1. If you notice that this one's multiplied by 1, this one's multiplied by 1. This one has a 2 there. Okay, so it would be the first one, which is 0, the second one, which is 1, and then the third one, which is 2. So it's always going to be 1 off from that. And this doesn't actually really matter all that much for what we're doing, especially since we're going to infinity, but I'm just trying to be as exact as possible with this. Okay, from there, you are basically multiplying whatever this counter is by that delta x. So I'm just going to put a little delta x in there, and then we're going to do close parentheses here. So whatever the function is, the I, if you notice right here, it's 0 because it's I minus 1. So if you plug in 1, it's just going to be this 1 right here. If you just plug that in for the first rectangle, it's 0. So there is no additional part right here. But the other ones all have that. If you notice, we have one here and we have one here. If you plug that in, it kind of makes sense. Then it all multiplies by that delta x. If you notice, we have the delta x here. We have the delta x here, we have the delta x here. So, and you also notice it for all these other ones too. So what we're just going to do is multiply by delta x. Okay, now what this basically allows us to have is a sum notation for that integral that we had originally. So if I zoom out really quick here, you notice that we have this integral part right here. It's the area underneath this f of x function right here between the x-axis is equal to this integral notation. So that means it's also equal to this part down here. So I'm just going to kind of rewrite that real quick. So we end up having something like this. So now you can kind of see how one transfers to the other, how one can convert to the other. The one thing that's a little bit different here is this b right here seems to come out of nowhere. Okay, if you notice, everything over here is in terms of a and delta x. We have a. This you can see how this delta x becomes a dx with this integral notation. We have the function f and the function f over here, but this b comes out of nowhere. So to kind of simplify that, what I'm basically going to do is rewrite this instead of using this b. So let me get rid of this b really quick. I'm going to solve for b up here. So I'm going to solve for the b right here. And if you solve for b, you're going to end up getting b is equal to a plus n times delta x. So what I'm going to do, instead of having a b there, I'm just going to write a plus n delta x. N delta x. Okay, and there you have it. Basically, this is what you are going to need to be able to convert from integral to summation notation and summation notation to integral notation. Now, this is very abstract. Like I said before, I didn't really use any numbers to show how this works. So the next video I'm going to make, it's actually going to have worked out. It's going to be a worked out example using basically what we found right here. Okay, so if you have any questions about anything in this video, let me know.